Hello, so today we are going to do this problem called minimum number of vertices to reach all nodes. And so what the problem says is that given we want to find the smallest set of vertices in a directed acyclic graph that has n vertices, such that from this minimum set we can reach all the other nodes. So basically we get a directed acyclic graph and that contains n vertices, and we want to find the smallest number of vertices that can reach all other nodes in the graph, right? So let's take a look at an example and see how we can solve it. The input that we have is n, which is the number of vertices, and edges, which is the list of edges, and the format would be from 2, so we'd have 0, 1, for example, 2, 3, which would mean there is an edge between 0 and 1, and there is an edge between 2 and 3. So this is the problem. Now let's see how we can solve it. Okay, so let's see how we can solve this. So here I have an example. We have this graph. It's a directed acyclic graph. Now, how can we tell the number of vertices that we need here? So you could see, well, it's just 0 and 3, because with 0 we could reach 1, 2, and then with 3 we could reach 4, and that's pretty much it. There is no other node that can reach 0, so we would have to include 0 in the set, and there is no other node that can include 3, that can make us reach 3, and so we would have to include 3. And so the results for this example would be just 0 and 3. And so just from looking at this example here, we can automatically make an observation here. It's all the nodes that can be reached from elsewhere. Those have to be in the set, right? Because otherwise we won't be able to reach them. So a reachable nodes have to be in the set, right? Unreachable, of course, from any other nodes. And by unreachable here, it just means that they don't have a parent. 1 has a parent 0, 2 has a parent like 0 as well. So one way to interpret that is nodes that don't have a parent. Another way to look at it as well is if we talk in terms of in degrees and out degrees of a graph, if you have a node and then you have, let's say, 2 edges directed graph like this, 2 edges coming out of it, then this means that this here has out degree of 2. But if you don't have any nodes coming into it, that means you would have in degree equal to 0. If we take another example here, let's say we have this node that has another node coming into it, like this, and maybe 2 other nodes coming out, then the out degree of x here, the out degree of x is equal to 2, because we have 2 nodes coming out, and then in degree of x is equal to 1, because we have this here coming in here, so we have 1. If we had 2, it would be 2 in degrees. So essentially, for the unreachable node, we are just looking for nodes with in degree equal to 0, right? So this means that the smallest set we are looking for is just nodes with in degree 0. All other nodes that have in degree more than like 1 or 2 or more than that, they are reachable by another node, and that node would be reachable by other node. And this is true because because if you have it like this and it's reachable, then either this node is one of the unreachable and we would have included it, or there is another node until you get to the unreachable node. And so our problem boils down now to just finding the smallest set of nodes that have in degree 0. And so now let's see how we can solve that problem. So to find let's just write that down. So smallest vertex set of vertices reaching all nodes, right? a long name, sorry about that. And so we get n, and then we get the edges, right? This is the input. And so what we can do is just have a map that finds the in-degrees of all the vertices in the graph, right? So, and then after that, we can check and find those that are equal to 0. So the first step here would be of all nodes in the graph. And so to do that, we will need to define a map here. Let's call it in degree. So we can just use collections here. And we can make the default 0, right? Because that would mean that anything that is not in the map would have value by default 0, which means we can add 1 to 0 and just when we find the first in degree edge, and we would have just 1. So to do that, we will just go through the edges. So each edge has a from and a to. So let's just call them maybe from and to. From, to in edges. And now we will need to say, okay, in degree of 2, right? Because if you have from going into 2, that means that the in degree of 2 is 1, right? So the in degree of 2 is, we need to add 1 to it, right? And then now we would have the in degree, once we exit this, we would have the in degree of all the nodes. We can just return the, or maybe we could do a for loop instead. So we are going to just count all the in degrees that, just get all the nodes that have in degree 0. So to do that, we will need to return, so our set would be, we'll initialize it as res. We'll go through all the vertices in the graph, which are just in range of n, right? So let's call this v, since we are looking for vertices. Now, if the in degree of v is equal to 0, that means it's unreachable, so we'd have to include it. And so we could just add that to the append, actually, since this is Python. So we need to say append v, and at the end we could just return res. So very straightforward. Just calculate the in degree values. Those that are equal to 0, those are unreachable. We need to include them in the set, and that's pretty much it. Now, in terms of time here, we are doing O of E here, if we consider E the size of edges, and here we are doing O of V, right? So overall, the time complexity is O of E plus V time. So we can say this is linear for a graph, right? In terms of space, we are using just the in degree map and the result variable, right? So the in degree would be at most the number of vertices. Same thing for res. So in terms of space, we are just using the number of vertices. And that's pretty much it. Now let's just write this down and make sure it works. Okay, so I typed the solution here that we just went through. So just compute the in degrees, find those that are unreachable, which is equal to 0, and that's pretty much it. So let's run here on some examples. And all the tests pass here. This is of course not exhaustive, but this definitely should work fine on more test cases. Now we can simplify this a little bit. Instead of doing this for loop here, we could just return list comprehension, and so we could just say v for v in range of n, which is what we are doing below, but we want to return only if the in degrees is equal to 0. And we could just get rid of this, and this should still pass fine, and it does. Yeah, so we could also make this even with one in degree solution here, which is, sorry, with one line solution here in Python. Let me just write it down in a different method here. And so with this one, what we can do is we can just return. So with sets, we can do the difference. And so we could just get all the vertices, right? So a set of all the vertices in the graph. and from there we can subtract the nodes that have an incoming edge, right? The nodes that have in degree at least 1. And so to do those, we can just take v, right? Let's call it 2 from 4 from 2. Okay, let's just make this v actually. V is set because we can only make the difference between the set. So v for u and v in edges, right? So what this would mean is all the nodes that have an incoming edge, which means have in degree of at least 1, we are going to put them in a set and subtract them from all the vertices, which essentially is doing the same thing. And that should work in the same way. So if we run this, that still passes. And yeah, so that's pretty much it for this problem. The main idea is the smallest set that we need is the nodes that are unreachable or that don't have a parent, and from those nodes we'll be able to reach all those that are all the vertices in the graph. Yeah, so that's it for this problem. Thanks for watching and see you on the next one.